Welcome back to the deep dive. Today, we are going to try to visualize the invisible. We spend our entire lives on our phones, tapping glass, swiping screens, but we rarely stop to think about the absolute miracle of engineering that happens in that split second after your finger leaves the screen.
It really is a miracle. We take for granted that the internet just works. But underneath that simple tap is a massive, complex machinery that spans the globe.
Right. And to kick things off, let's start with this scenario everyone knows. You were scrolling through Instagram, you see a photo of your friend's new puppy, and you tap like, well, instantly the little heart turns red. But miles away, your friend gets a notification.
That's cool enough, yeah.
But my question is, what actually happened in the middle? Like physically, because it feels like magic, but we know it isn't.
No, it is definitely not magic. It is engineering. And what you were describing, that mysterious middleman handling everything behind the scenes, is what we call the back end.
The back end. I hear that term constantly in tech circles. Oh, he's a back-end engineer. The back end is down. But let's be real. What is it? Is it a cloud? Is it a supercomputer floating in the sky?
Well, to disappoint you right out of the gate, at its simplest level, a backend is just a computer.
Just a computer.
It's a server. But it's a computer with a very specific, very stressful job.
Yeah.
It is sitting there, usually in a massive, freezing cold data center, just listening.
Listening, like literally listening.
Metaphorically. It has these digital doors, which we call ports, and it is just waiting for someone like your phone to knock on that door and say, hey, here's some data, or hey, please send me a picture of that puppy.
Okay, so it's a computer waiting for a knock. I can picture that. So for today's deep dive, our mission is to trace that knock. I want to follow the physical journey of a request from my browser all the way to this mysterious server and back. I want to know where it goes.
Let's do it. We can trace the path.
All right, set the scene. I open my laptop, I open Chrome, and I type in a web address. Let's use the example from the reading material. sreniously.xyz. I hit enter. What is the very first thing that happens?
The very first thing is that your browser has a bit of a panic moment.
Why?
Because it has no idea where sreniously.xyz is. Computers don't speak English, they speak numbers. They need coordinates. Imagine getting in a taxi and telling the driver, take me to the cool bar. The driver's going to look at you blankly until you give them a street address.
Okay, so the browser is the confused taxi driver.
Exactly. So step one is the DNS, the domain name system. Your browser shoots a frantic message out to a DNS server, which is basically the internet's phone book. It asks, where does sreniously.xyz live?
Yeah.
And the DNS server looks up the record and replies with a numeric IP address, something like 192.0.2.1.
Okay, so now my browser has the address. It knows the destination is, say, an Amazon data center in Northern Virginia.
Precisely. And this is where the physical journey really begins. That request leaves your laptop, goes to your Wi-Fi router, travels through fiber optic cables under the street, maybe even under the ocean, depending on where you are, and arrives at that data center.
So we are the data center.
Yeah.
Rows of servers, blinking lights, loud fans.
Yeah.
My request walks up to the specific computer we found in the phone book. Can't just walk right in.
Absolutely not. That would be incredibly dangerous.
Why?
Because the internet is a hostile place. I mean, there are bots and hackers constantly knocking on every door of every server, trying to find a way in. So before your request even touches the server application, it hits the firewall.
The bouncer.
The bouncer, but a bouncer who is seeing millions of people trying to storm the club every second. This cloud server is protecting itself. It blocks almost every door or port. It only leaves open the ones meant for public traffic, usually port 80 for standard web traffic or port 443 for secure traffic.
So the bouncer checks my ID, sees I'm just looking for the website on port 443, and lets me through. So now, do we hit the application code yet? Are we talking to the brain of the back end?
Not quite yet, and this is a detail a lot of people miss. If you walked straight into the application code, you might crash it.
Really? I thought the whole point was that the code handles the request.
It does, but application code, whether it's written in Node.js, Python, or Ruby, is often, like, brilliant, but very easily distracted professor.
Okay.
It's great at solving complex problems, but it's terrible at multitasking or dealing with slow talkers.
Slow talkers.
Yeah. Imagine if 1,000 people called that professor at once, and some of them had bad cell reception and were cutting out. The professor would get bogged down just trying to hear them, and no actual work would get done.
That makes sense. So you need someone to screen the calls.
Exactly. You need an executive assistant.
Yeah.
In the tech world, we call this a reverse proxy. In our source material, the specific software used is Nginx.
Okay, so Nginx is the assistant.
Right. Nginx stands at the front door. It's incredibly fast and can handle thousands of connections at once without breaking a sweat. It takes your request, handles all the messy connection stuff, and says, okay, this person is legit, they want the user data. Then, and only then, does it pass the request internally to the professor, the actual application server.
So Nginx is the shield.
It is the shield and the traffic controller. It passes the request to a local port, usually something like localhost 0.3000, where the actual backend application is running.
Localhost, I see that on developer screens all the time.
It just means this computer. Nginx catches the request from the outside world and hands it off to the program running locally on the same machine.
Got it. So now, finally, we are with the professor, the application server. This is the Node.js or Python code.
Yes. This is the brain. This is where the logic lives. It takes the request, figures out what you want. Maybe you ask to see that list of comments on the puppy photo, and it prepares a response.
And what does that response look like? Is it sending me the whole web page, the colors, the fonts, the images?
Usually no. If we are talking about a modern app like Instagram, the back end isn't sending the look of the page. It's just sending the raw facts.
The data.
Right. It bundles that data up into a text format, most commonly something called JSON, which looks like a list of key-value pairs. User, John, comment, cute dog. It hands that text back to Nginx, which hands it back through the firewall, across the ocean, and finally, your browser receives it.
And then my phone takes that text and turns it into the pretty interface I see.
Exactly.
It is incredible when you break it down like that. But this leads me to a question that I think a lot of people have, especially now.
What's that?
Why do we need to do all of that? I mean, I have the latest iPhone in my pocket. It has a neural engine. It has gigabytes of RAM. My laptop is more powerful than the computers NASA used to send people to the moon. Why can't the app on my phone just do all the work? Why do we need this centralized server miles away?
That is the million-dollar question. Why not just put everything on the front end, the phone?
Exactly. Cut out the middleman.
There are 3 really critical reasons why your phone simply cannot do it alone. The first one is centralization. Let's go back to your Instagram like.
Okay.
If you tap like on a photo, that information changes the state of that photo. It now has one more like. If that logic only happened on your phone, who would know?
Just me. My phone would know I liked it.
Right. But your friend needs to see it. A stranger in another country needs to see it. Friend 10s are distributed. Everyone has their own copy of the app, their own little island. But the data needs to be shared. You need a town square.
Town square.
You need a central authority, a single source of truth, where that like is recorded so everyone else can fetch the update. That central place is the back end. If we did everything on phones, we'd have millions of separate lists of likes that never matched up.
Okay, that makes sense. You need a referee to keep the score.
Yeah.
But what about something that doesn't need sharing? Why can't I just run the code on my phone for my own stuff?
That leads to reason number 2, which is probably the most important one. Security.
Security. But phones are secure. I have Face ID.
Your phone is secure, but the environment the code runs in, the browser or the app, is what we call sandboxed.
Sandboxed. That sounds safe.
It is safe for you, but it restricts the code. Think about it. When you visit a website, your browser is downloading code from a stranger's server and running it on your machine. If that code had full access to your computer,
It could steal my files.
it could read your emails, look at your photos, steal your passwords. So the browser puts that code in a sandbox. It says, you can play here, but you cannot touch the user's hard drive. You cannot look at their other open tabs.
Okay, so the front end is handcuffed for my own safety.
Exactly. But a backend. The backend runs on a server we control. It is not sandboxed. It has full access to the file system, to logs, to memory. But more importantly, it can keep secrets.
Secrets.
Imagine you have the master password to your company's database. If you put that password in the code running on my iPhone,
I could find it.
you could just plug your phone into a computer, inspect the code, and steal the keys to the kingdom. You never, ever trust the client. The backend is the vault where the secrets live.
Okay, so centralization and security. The sources mentioned a third reason, something called Core RS.
Yes, CoreOS, cross-origin resource sharing. It sounds technical, but it's actually about identity theft.
Identity theft.
Browsers are very paranoid. If you are logged into your bank's website, your browser has a session open. Now, imagine you open a new tab and go to sketchy-site.com.
Okay.
Without strict rules, the code on sketchy-site.com could try to talk to your bank's website in the background and say, hey, send $1,000 to this account.
Right.
And since your browser is logged in, the bank might think it's you.
That is terrifying.
It is. So browsers have a rule.code from one website cannot talk to another website unless the second website explicitly says, I know this guy. That's CORS. But backends, they don't have browsers. They don't have users clicking around.
So the backend can talk to whoever it wants.
Exactly. A backend server acts like a diplomat. It can securely talk to Stripe for payments, Twilio for texting, and Google Maps for location, all without the browser's restrictions. It bridges your phone to the rest of the digital world.
Okay, so we've got the concept, but I want to dig into the mechanics of the heavy lifting. The source material made a really interesting point about databases.
Right.
I always assume that when I use an app, my phone is just saving data to a database somewhere. But you're saying I can't just connect directly.
Technically you could, but practically it would be a disaster. And it comes down to a concept called connection pooling.
Okay, help me visualize this.
Imagine a very popular restaurant. The kitchen is the database. The chefs are the database process. Now imagine if every single customer who walked in the door didn't just sit down and order, but actually marched into the kitchen, put on an apron, and tried to tell the chefs what to cook.
It would be anarchy.
It would be total chaos. The kitchen is small. It can only handle maybe 50 people at once. If you have 10,000 users on your app and they all try to open a connection to the kitchen,
The kitchen explodes.
the database crashes. It runs out of memory immediately.
So how does the backend fix this?
The backend is the waitstaff. It hires, say, 50 waiters. These are the pool of connections. No matter how many thousands of customers are outside, only those 50 waiters are allowed in the kitchen.
So the backend takes my order, waits for a free waiter, and sends them in.
Exactly. It manages the traffic. The waiter goes in, gets the data, comes out, gives it to you, and then this is the key. The waiter doesn't go home. They stay ready for the next customer. That is connection pooling. It protects the database from being crushed by the users.
That makes so much sense. We are protecting the most valuable resource, the data, from the volume of the crowd.
Precisely. And the same logic applies to computing power. Your phone battery is limited. If you try to do heavy video processing or complex math on a cheap Android phone from 5 years ago, it's going to freeze.
Or catch fire.
Possibly.
Yeah.
But the back end. We can rent a server with 100 processors and terabytes of RAM. We can guarantee the work gets done fast no matter what device the user is holding.
So we are offloading the brain power to the cloud to make sure everyone gets the same experience.
Right. Consistency.
I want to go back to the professor for a second, the application server. We left our request sitting on its desk. But a back-end code base can do a million things. It can log you in, delete a post, update a profile. How does it know which one to do?
That is the concept of routing.
Routing.
Think of it like sorting mail. When a request hits the code, the server looks at two things, the address and the intent.
The address is the URL.
Right, the path, like users or photos.
Right.
But the address alone isn't enough. The server also needs to know the intent, which is what we call the HTTP method.
Method.
Is it a GET request, meaning I want to see this data? Is it a POST request, meaning I want to create new data? Or a delete request?
So I could send a request to the photos address, but if I send it as a delete, the server knows I want to erase something.
Exactly. The router looks at that combination delete plus photos and sends it to a specific function in the code called a handler that knows how to delete files.
It's literally a mailroom. This package is a return, send it to returns. This package is an order, send it to shipping.
That is exactly how it works. And once that handler runs, it needs to save the result. And this brings us to the final piece of the puzzle, persistence.
The sources distinguish between two types of memory here, RAM and disk. I feel like I hear these terms used interchangeably by non-tech people.
Yeah.
What's the actual difference in the backend?
The difference is what happens when the power goes out.
Okay, high stakes.
RAM primary memory is incredibly fast. It's what the server uses to think, but it is volatile. It's like your short-term memory. If the server restarts or crashes, anything in RAM is gone. Poof.
So if I wrote my essay in RAM and the power flickered?
Start typing again. That's why we have secondary storage, the disk, hard drives, SSDs. This is persistence. It's slower than RAM, but it writes the data into the physical material of the drive.
So the database lives on the disk.
Yes. The database's job is to take the data from the fast, dangerous RAM and safely write it to the slow, safe disk.
So the backend engineer has to balance this.
All the time. In fact, we often use something called caching. We keep a cheat sheet of popular data in RAM using tools like Redis so we can answer quickly. But we have to be very careful to make sure that eventually that data gets written to the disk.
It's like taking notes on a scrap of paper during a meeting. because it's fast, but making sure you file the official report in the cabinet before you leave for the day.
That is a perfect way to visualize it.
So we have traced the journey. We have the browser finding the IP via the phone book, hitting the bouncer at the firewall, and Jinx the assistant shielding the professor checking the mail via the router, and finally the waiters in the kitchen getting the data from the fridge.
That is the full picture.
It is a massive, complex system, and honestly, it sounds exhausting for the computers involved.
It is. But it's designed to be robust. It's designed to handle millions of people doing things simultaneously without the whole world crashing down. It connects the distributed senses of the frontal soul, those phones acting as eyes and ears, to a centralized brain.
The back end is the brain. I like that.
Mm.
And here's where I want to leave our listeners with something to chew on. The source material touched on a pretty heavy concept at the very end.
About fragility.
Yes. We have spent this whole episode talking about how great it is to have a centralized source of truth, a single brain. But isn't that also a massive risk?
It is the ultimate risk. If the back end is the only place the truth lives, what happens when that single point of failure goes down?
If the brain stops working, the body stops moving.
Exactly. We built the system to be efficient, but we also built a choke point. If that data center in Virginia loses power, or if someone cuts the fiber optic cable, the app on your phone becomes useless. It's just a shell.
So what is the solution?
That is where modern engineering is going now. Distributed systems. We don't just have one brain anymore. We are trying to build a hive mind. We replicate databases across continents. We have clusters of servers. We are trying to build a brain that can survive losing a chunk of itself.
Which sounds like science fiction, but I guess it is just the next layer of the problem.
It is. It's about fault tolerance. How do you build a system that is reliable even when the individual parts are unreliable? But that is a rabbit hole for another day.
It certainly is. For now, next time you tap like on a photo, take a microsecond to appreciate the journey the request is taking through the bouncers, the assistants, and the chefs, just to turn a little heart red.
It really is the invisible miracle of the modern world.
Thanks for listening to The Deep Dive. We will catch you on the next one.